Sandesh, I have the pleasure of introducing Sandesh. I've known for a while. He's another fellow Oracle guy. He's the VP running the AI ops automation. So all of the automation, all the ML that's inside the database that you see that gives Oracles the ability to do these amazing things with a database. That's his area. So he's going to be kind of lifting up the hood a little bit and showing you a little bit of what's going on underneath there, how they do that. And with that, I will get out of his way and let him take it away from here. Sandesh, the floor is yours.
Sweet. Well, after all these awesome presentations from Phil, Philip, and Barry, I think this is going to be a hard one to beat. But hopefully
I don't think so. I don't think so. We saved the best for last for our 3-hour tour.
I'm really enjoying all the trivia questions here. I think that's probably more fun than the presentation. But all right. Let's see. Let me share the screen. I'm going to.
Oh, I gotta stop. Stop sharing. There we go. Floor is yours.
All right. Thank you, sir. Well, much appreciate you guys giving the opportunity to present. This is a slightly different angle. So most of the other presentations, I showed you some of the examples of what people do with Oracle machine learning and some of the other Oracle analytics and all these stacks, right? My role is slightly different. I'm actually responsible for this thing called AI Ops, which is basically taking all of the infrastructure at the back that's behind the autonomous database and trying to manage it. This is the reason why this is a managed service and you guys do not see too much of the stuff that you have to do with the service. You just log in and you just go ahead and use the service. So what we do is we have close to like 100+ examples across all sorts of different stacks. And I just kind of randomly picked a few examples that I'm actually making as part of this presentation. All right, let's go. So here's kind of a rough theme. What we're going to do, we're going to talk a little bit about the AIOps architecture and use cases. We're going to spend most of the time on the use cases. And then we're also going to talk a little bit about which algorithms, tools, technologies, and if we have any time for open talk and questions. All right, everybody knows this. And why machine learning is really cool. It's like one of my colleagues is a statistician, and she basically told me, you computer science guys know how to make things cool. So until like just a couple of years ago, statistics and stuff like that, and people look at it and say, oh, this is all math, and they just kind of scamper off in the other direction. But now all of a sudden, machine learning is really cool, and everybody wants to get into machine learning, whether whether they know math or not. And as you've seen, many of the folks, presenters before, have actually shown techniques of how it's possible to get started with machine learning very easily without really having to understand most of these mathematical algorithms or how these algorithms actually work. So one of the reasons why most people are in this space today, data scientist jobs are lucrative. A lot of data is lying around and people really don't know how to make sense of it. So now there's all these algorithms, platforms, and libraries that are available for you to just kind of download and do a simple Docker in it, and you can get started with most of the stuff. You can just initialize an autonomous data warehouse instance and just a couple of clicks get started with some Zeppelin notebooks. So you saw Barry talk a little bit about that. And you saw Philippe talk about how you can use OSC for that. So the entry point for this stuff is really easy now as compared to what it used to be like a couple of years ago, where you really needed to know the algorithms and how this thing was distributed. So there's basically in AI ops, right? There's 3 strategic pillars. There's install, upgrades, there's patching, there's dependencies, there's SLA management, placements, and stuff like that. But most of what my team concentrates on is the stuff on the right-hand side, which is basically fault detection, root cause analysis, SLAs, health dashboards, prediction of workloads, prediction of capacity management related issues across data centers, across the fleet that we have for the autonomous database. So I just spent a little bit of time trying to talk a little bit on the overall architecture of this, and then we'll dive into the use cases where we use machine learning, which is actually the most interesting part of this presentation. So the first thing is, most of our training basically happens in the lab. So this is applied machine learning, where we take a whole bunch of inputs that we get from the logs, from the defects that we have, and we analyze them, we pick the right attributes, we train our models, and we push them. We'll go into a little bit more details of these models as we go through our use cases. Once we have these models, we push them off to the machines, the Exadata boxes where all these things run, and then they basically, only a certain category of messages are basically sent across to the user using the customer notification service. Otherwise, everything is scaled out using the object store. And then we have the AHF service, or the Autonomous Health Framework, which is what my team is responsible for. And what that does is it basically takes all this data and massages it and applies different algorithms to it. And depending on what is in this content, It either triggers rules, notifications, pager duty, or just generates dashboards and visualizations for people to do. This is a very, very simplified chart of what we have in every data center that's basically running, that allows a small number of cloud ops people to basically manage an entire data center full of Oracle databases. What are the sort of data that basically is involved in this? If you're having an Oracle database background, there's basically alert logs, which is log data. The log data is actually one of the highest chunks of data that basically comes into this thing. And then there's metric data. There's performance data, availability data, health data, capacity data, compliance data. All of this stuff basically gets pushed out as part of the telemetry that gets generated from the system. And all of this gets pushed off to the object store, and then we read it from the object store. One of the reasons we use the object store, so we use a combination of an object store and a notification service, which is basically like a Kafka kind of a service, and that pushes all this information across multiple data centers. So we can scale the service from one data center across multiple ADs and push it across multiple data centers and stuff like that. So this is really powerful, but this is sort of the data that is behind the scenes here of what is used for most of the machine learning services, which is located in the control plane. So this is the DOM view of the machine, and this is all the various kinds of data that get pushed, and those are the tools that we use internally to push all this stuff out to the TFA service. Examples. Now, these are, so we have more than 100 plus projects, and what I try to do is every time I try to present this, I take a combination of examples, and it's like it sometimes takes longer to kind of prepare a PowerPoint on these things as compared to like the actual examples themselves, which are a couple of weeks to build and train these models and kind of deploy and ship them out. So the most interesting one for me, and this is something that kind of takes the most amount of time, anybody in IT will relate to this very, very easily, is called the anomaly timeline. Now, anomaly timeline is a very overloaded term, and today everybody uses this term, but it means different things to different people. In this case, we're using anomaly timeline for scanning a whole bunch of log files and trying to basically eliminate things that are not interesting from these log files. So this is complete text-based mining. And we use all sorts of different methods, and I'll go into details of how we do this. But the goal is, like, imagine I have a 40 gigabyte log file and I want just like 400K of content from it. And all the rest of the stuff is actually not interesting. So how do you take all this content and push this data out so that you can build a simple lexicographical analysis based on a time sequence? So you can look for spatial as well as temporal related errors. So if something happened in this component, is the other component functioning fine or not? As well as it's a simple classification clustering model that's used to actually do all of this. How do we do this? Yeah.
Hey, Sandesh, a real quick question, because this came up with some customers that I was with recently. This is all software, or is this also hardware?
No, this is all software.
Yeah, okay.
This is completely software. So we've got the ability to take the logs, we can analyze them, we can clean this and cluster the stuff up to generate a model, and then this is shipped. This is shipped basically to the autonomous health service, which sits in the control plane. Now, the things that this thing identifies is it identifies log anomalies, metric anomalies, as well as combines both of these things into a single anomaly timeline. Now, you can make analysis, you can take this analysis and actually push this out to bugs and SRs. So this is also used automatically for cases where the ops team in the back is basically looking at failures that are happening across systems. Remember, we got thousands of databases in each data center. And it's not possible for a DBA to basically sit and eyeball and look at each and every exception and try to figure out, oh, here's the timeline of sequence of events that have happened, and how do you take care of this, right? So for people that have managed on-prem databases can understand how complicated it is when something goes wrong, and then you're trying to piece something from the OS, from the Exadata side, from the database side, and you kind of make a single picture of what this thing actually means. So there's different kinds of technologies that are used to make this end-to-end thing work. So let's start off with what the use case is. You take logs, you identify them by different kinds of file type classifications. You parse this data and you try to identify the anomalies. So the label outcome for these things in a classification model is this line interesting or not? Or is this an anomalous entry, or is this a normal log entry? And then you take all the anomalous entries and you line them up using an anomaly timeline. So it's very easy for an ops person to say, this is the problem, this is the fault, this is what I'm supposed to do, click on this, fix it, or fail over these customer sessions automatically to this particular instance, because this system is not going to recover based on these things. So it's a combination of using anomaly detection to come up with this and applying an expert system or a rule-based system on top of this anomaly timeline to create some kind of an adaptive baseline to trigger automated actions across the data center. So how does this actually work? So This in itself is like a 1-hour presentation. I'm trying to condense down. I'll give you the quick details of this, of how it works. So there's basically log cleansing. So you take the logs, you split them up, you string tokenize it, and then you basically pull out the invariants, which are instance IDs, process IDs, database instance name, Exadata box name, all of that sort of stuff that's actually different. And then you do the entry feature creation. In this case, you look for log entries, you look for hosts, you look for, you basically define attributes, right? So using PCA to define the attributes here. And then you do entry clustering to find out which log entries look similar to the others. So for example, there are 2 kinds of OR600s, and they just differ by 1 argument, but that might make the entire difference where these 2 lines are no longer similar. But some of them have 2 arguments, and the second argument is the only one that's changing, but those lines are similar. So we use that to generate, to do clustering for these kind of exceptions. So the exceptions that cause similar kind of outages are grouped together. That's the whole idea to do this entry clustering. Then we generate a model. This is a simple decision tree model. And there are different methods to do this. The entry clustering and decision tree model generation, we used to use something called sequence matcher earlier to kind of match together lines and perform like anything that's, anything that's more than 85% similarity is classified as a similar line, otherwise we throw it away. So this is a combination of using sequence matcher. We've replaced sequence matcher ever since with something called cosine similarity because it's a lot more faster. So it's cosine similarity to identify and compare against lines and find out which line is the same as the other. And the next one is we also use k-means to cluster these lines together once we have identified these invariants. And then from there, we take expert input. Now, what is expert input? Expert input is the developers. The developers actually look at these log files. They look at these log files and say, this log file entry is interesting, this log file entry is not interesting, this is what I would look at if I would be debugging this problem. So you take all this stuff and you combine them and you use this for expert input. So this is truly a semi-supervised machine learning example. And once you do this, you create a knowledge base. The knowledge base is basically as an outcome of this decision, the decision tree classifier. And then you index it so that you can actually scan against live log files. Now, the thing that's always been a challenge for us, building this model was not exactly the easiest thing ever, but once we built it, we had to scale this model. And you had to scale this model for billions of log lines and come in every couple of minutes. So how do you do a fast Cartesian product of a whole bunch of log line entries against a knowledge base and try to make this in such a way that's near real time without actually having to consume a copious amount of CPU? It's a very interesting problem. So the simple answer to this whole thing is once we have the model, we use TF-IDF to basically rank and perform correlation for these things. And what TF-IDF does is we generate a score for every token that's part of the log file entry. So when the log line comes in, we know that some of the TF-IDF scores of the entire line. So like, it's like, I'm trying to do something X. Every word of these is classified and the sum of it is generated. If that score is less than a certain value, then that line does not get matched against the knowledge base. That's how we identify log entries that are interesting and not interesting, and then we match them against the knowledge base. And to reduce the Cartesian product that happens between the incoming log lines and the knowledge base, we use TF-IDF to filter out the lines that are not that interesting. So once we build this knowledge base and deploy this, we can look at issues happening in our data center pretty much near real time without actually having to look at all the logs that are generated by our databases. Just to give you an idea, a single database in an Exadata box can generate about 8 gigabytes of data an hour. So we're talking about like 2 or 3 months of data can run into 20, 25 petabytes. So it's a lot of data that actually the system has to go through. So we're reducing this data to come up with a simple timeline that basically tells us these are the interesting things, these are the systems that are happening in, these are the log lines that are located. So if I'm an ops person, I can click on that single line and it directly takes me to that log entry that corresponds to that fault. And I can look at things around it. Now, so people are like, okay, so you're taking a bunch of log inputs, you're breaking these things up, you're string tokenizing them, you're generating a decision tree out of this, and you're comparing log lines that are coming in from incoming logs, and you're doing a Cartesian product sort of a thing to find out which log entries are interesting. But where's the machine learning kind of in this? The machine learning helps us identify anomalous and non-anomalous entries. Okay, that's interesting, but how do you take this to the next level? How does this look any different than an Elasticsearch Kibana kind of interface, right? We're just taking a bunch of log lines, building this giant index, and you're trying to scan and look at all these things. The key thing is, it's the data filtering that's actually interesting, which is what we have, where we can actually look at just the entries that are interesting to our developers. But not just that, you take it to the next level and you can actually merge different kinds of data. So you're talking about, as you can see, this is failures coming from 3 different components, right? So there's database, there's clusterware, and there's VMstat data. So you're trying to simultaneously take 3 different metrics and you're trying to highlight these faults, and you're trying to highlight them in a sequence, in a timeline where you can kind of make sense of it. So any metric that can be in a time series can be massaged. You can calculate, mean, median, max, t-test, f-test, any such kind of metric, and you can slap this into a timeline. So while I'm looking at a fault and I'm like, what was the CPU utilization on that machine at that time? And is it normal or not? Because there's no way for me to know, right? I'm looking at hundreds of thousands of database instances. There's no way for me to know if a CPU utilization of a box at 90% is normal or not for that particular user at that time of the day, because I have no idea who this user is. It's very easy in an on-prem environment. Oh, Friday morning, Fred runs a report because his wife kind of goes to the grocery store and he gets bored and he just comes to the office and runs this report. So I'm a DBA, I know this. But if I'm running this in the cloud, I don't know this. So I want to know what this value is. Is this value normal? So this is where the VMstat data comes in and it combines it as part of the anomaly timeline. So this is pretty cool for us. So this is the first use case where we can take all this data, we can build a timeline, and we can kind of massage all this information together. Second use case, what is the CPU utilization? So when you're packing a whole bunch of instances in a particular system, you monitor the AWR ash data, and then you try to predict resource usage. And then what you do is you also identify anomalous SQLs or SQLs that have had plan changes, and you correlate this with workload as well as resource usage. The whole idea behind this for us is to find out which tenants in a shared environment can be packed in the same instance. How do you predict capacity shortages? Like say, for example, if I'm a payroll guy and I pay people on the 15th and somebody else pays people on the 16th, we're compatible and we should be put in the same instance so that we're not going to have the noisy neighbor problem and consume resources at precisely the same time. So this is kind of making things smarter for us from an ops perspective. How do we do this? We take the capacity data and then we apply Holt-Winters to this. So simple triple exponential smoothing. So the first level, what you're doing here is you're basically taking a time series. In this case, it is core CPU usage. And then you're forecasting this using an exponentially decreasing weighted average of all the previous data points, which means anything that is recent has a bigger impact on the forecast. Then what you do is you have to normalize this information because there are a lot of spikes back and forth. Boxcox is one such method, but there are many, many methods of doing this. But Boxcox is one method where you can actually prevent the distortion of these impacts of these spikes on the overall thing, and you get kind of a smooth line and you know where the actual faults are located and where those faults are consistent. So this is the first phase. And then you calculate the trend between each of these observed data points. Again, so the more recent the trend, the bigger the impact it has on the forecast. The whole idea also is to dampen the trend. So linear trends, right, if you have, they tend to overestimate. So we add a dampening factor, which is a parameter to basically, forecast and trend this eventually to a flat line. It's more useful to add this when you're doing something like long-term forecasting for, say, in this case, CPU utilization. The third one is to look at seasonality or repetitive factors, right? So you're applying a seasonal component so that you can basically find what the actual residual values are, which is typical of any time series-based analysis. So again, once you apply this, what you land up getting is any fault that happens. You basically look at the forecast, you calculate the errors. You're obviously taking RMSE, so it's always a positive number. And you basically calculate the mean of all these square errors to get an average. And you're trying to calculate the errors at each level when you're stepping through. The last stage is, this is kind of like what the output of the algorithm looks like, right? So I'm looking at different instances. I'm looking at the blue, which is basically the CPU utilization today. And then I'm looking at the green, which is the predicted CPU utilization. Remember, the idea is to trend to a flat line or to try to go to an as consistent curve with consistent seasonality over a period of time. Will it actually turn out to be that? No, but this is kind of like how the prediction algorithm works. The red line is basically what we expect the mean to be, or the highest values at that point. Sorry, the red line is the highest value at that point, and the green line is what you expect the thing to be over a period of time. So this is, depending on the core sizing we have for the instances, we can predict, oh, if I'm going to put a few more clients on this machine, how much more is the CPU utilization going to trend towards? The more I trend towards the red line, the idea is to push the next set of clients into another set of instances. The third use case, how do you find the best maintenance windows? So there's different kinds of maintenance windows in the Oracle parlance. One of them is applying patches, which sometimes requires downtime, like you're doing a major database upgrade. The downtime is pretty significantly less, but there's a lot of tiny things that you can run where you can apply SQL patches, you can run some SQLs, you can collect stats, all of these things. You can do some maintenance on one of the Exadata cells while the rest of the cells take over the load. You try to figure out what are the maintenance slots. A very good example of this is, you just take your phone and you keep it down at night. It knows when you're not using your phone and it goes ahead and patches the phone automatically. And then next day morning, you're like, oh, the phone has been updated. So how does the phone know you're using it or not? Basically based on the gyro, a couple of your usage characteristics, the apps, the flow, so it knows this is the time you use the screen. I've tried to trick my phone a couple of times to picking it up at 2 o'clock and 4 o'clock in the morning, but it still manages to patch itself in the morning when you're done. So this is kind of like, if you're trying to, a good example is if you're trying to change pavers in front of your house and you're having a party inside, what's a good time to do this? And what are the various characteristics you will do? So you got to ensure that you have some great entertainment, you have a barbecue, you have the beer, you have a movie going on inside so that people don't bother coming out and you can quickly change the pavers. So when do people walk in? When do they walk out? What is the entertainment characteristics inside the house? So this is sort of like an example of what, and the whole motivation behind this was, we wanted to run a bunch of scripts on our application and we want to find out when's the best time to do this. And as you know, there is no downtime nowadays because every database in our case gets used every time across the world, somewhere or the other. So we ran this very simple algorithm. Now, the one we finally developed was a lot more complicated and has a lot more variables to it, but this gives you an idea of how you can do this if you want to do this yourself for your own on-prem databases. You take the original data, you apply a convolutional filter, you average it out, you apply seasonality, calculate the residual value, and then you find the position in the seasonality for the best and the worst maintenance periods. So according to this, at 8 o'clock in the morning is the worst time to run anything. At 7 o'clock in the evening is the best time to run anything. And this, you do this over a 7-day rolling window of data. And this will basically give you what is a good time to apply or do some kind of activity. The actual version we have in production even goes down to like 5-minute windows. So it'll say, okay, it's like, people who try to have meetings, they're like, okay, I've got a 5-minute slot here, I've got a 5-minute slot there, and you try to match your slots as you go, right? So this is basically what the algorithm does. It creates slots, it matches slots together, and it also looks at the activities in those slots. So like, for example, I want to rebuild an index. Oh, do I do this at this time? Oh, if that time I'm running SQLs that query the index, then that's not, even though I have a free time, it's not a good time to run the index rebuild because I'm running a SQL that might actually query the index that will degrade my performance. So not only is the time prediction important, it's also the activities that are run within those windows and if they conflict with the nature of maintenance that you're actually doing. So this is a very, very interesting example. At some point, if we perfect this, there will be no maintenance window as far as visible to a customer. Even major database upgrade windows will basically disappear. But the truth of the matter is, customers always love to know when their maintenance windows are so they can just send their people home and say, okay, nobody's going to page me in the middle of the night. So I think as a human, we still have to move to a point where enterprise systems can be transparently patched completely 100%, where you don't really care about what kind of maintenance is going on and what the maintenance window really is. Today, the truth of the matter is, more than 80% of people love to know when their maintenance windows are so they can send their users home and they don't get paged at night. So it's more of us humans have to change to this mentality. But I'm hoping this at some point will be so good that we don't really care about downtime anymore. And most of the Oracle components supported anyways. This is an interesting one. So this is unusual OS metrics. So this is something we use called z-scores. It's a simple standard deviation from the mean, and it basically allows you to compare apples versus oranges, CPU usage versus IO wait time. So metrics that can't be compared, we compare against these things. And we don't use this to pinpoint the details of the anomaly, but think of this as a red, orange, green light. So any machine that has a combination of various things that are not going right, the machine gets flagged, and then we use some of the other methods I described earlier to go into the depth to find out what's actually going on. Here's a simple example, right? So we've got CPU utilization, original metrics, not comparable, so many spikes. And then you apply z-scored metrics, where you scale the values up. You're kind of running them at the same scale. And you look at these values, and now the larger spikes basically show up. In the previous graph, they're at different scales. So you cannot see if the scale for something that generates too much noise is too high, then you can't really see and compare this against something else, which is small, but it's actually having a much more higher impact than a spike that's actually large. So that's what these z-score spikes help us to do. But what's the whole idea behind this? Why would you use this, right? So there's a whole bunch of stuff that happens over a period of time, from CPU utilization, IO related issues, something, the processes are going uninterruptible sleep, things that are not being pushed onto the Exadata cells for storage indexes. There's like, if you look at this list, there's a list of probably like 300 plus metrics that get constantly compared against to find out if a box is actually having a problem or not. Now, if you look at a graph, this is sort of like what it looks like, right? So for z-scores for each and every one of these things, of course, for the purposes of simplicity, I've only put 6 of them, but this actual graph can have 250 different variables. The idea behind this is you basically combine and find the periods where there's multiple events happening at the same time. That's the whole idea, is you combine this to look at if there's too much stuff happening across too many components at precisely the same time, there's something wrong with the box. That's all that this use case helps us identify. Boxes, when I go into the data center, I look at this console with all these events happening, and I'm like, which machine should I look at first? There's just so many problems. Instead of that, what this does is it prioritizes, like, which is the first 5 exadatas I should look at to fix the problems in the data center if I'm an ops person. If you go with paging, I could have 50 pages. How do I start? How do I know this page is more important than this page? This is what helps us identify that. It basically takes all of these things and puts them together and says, these are the things that have a high z-score, and there's multiple things going wrong at the same time. There's probably a higher chance that this box is probably going to go down, and that's what we use to predict. That's the third use case. The fourth one, and this is something that has the most amount of impact for us. It's a trivial use case, or it seems like that, but it's actually the one that has the most amount of impact for us. Everybody that has used a database knows when something goes wrong, you're going to download a patch from my Oracle support and patch your instances. But how do you know what patch to apply? How do you know what the issue is? You create a service request, engineer comes in, looks at your logs, says, yeah, this is the same problem. Click and download this patch. You click and download the patch, schedule a piece of downtime, install the thing on your system, done, great. And then the cycle keeps repeating again as you keep finding newer problems. It's great if you have 50, 100 databases. The moment you start running into 1,000 plus databases or hundreds of thousands of databases, it might take 3 months to patch all of these database instances if you do it using the same manual method. So this method doesn't scale. So how do you do this, right? So we take all the logs using the previous anomaly detection method, except in this case, we have a different model for this. And we've built something called Adaptive Bug Search, or ABS. And this product or service within the Autonomous Health framework, it takes more than 400 plus Oracle products, and it performs simple logistical regression on this to train and generate something with a model. And it provides 8 possible duplicates per bug or service request. Now this depends. If it knows for sure if this is a problem and this problem has this signature and the signature kind of matches, it closes the request and automatically that particular instance gets scheduled for a patch application. And the patch application automatically finds its own window and it'll upgrade that database application when the user is not affected by it. That entire cycle for more than 80% of the bugs is automated. So there's no human involved in this, and somebody takes a look at it, oh, this is matched, okay, this is the duplicate, click, 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 done. So I could have 10,000 databases having problems, and only 2 of them might actually be problems that are not resolved yet. And the remaining, say, 5,000 problems that are raised might be something we already know of. There's already patches available out there. But so it's a waste of time for somebody in ops to look at it and say, yep, know this problem, yep, know this problem, yep, know this problem. And when you're at 4,999, you're like, yep, know this problem. It's time for me to go home. And then you miss the 2 problems that you actually need to look at. And the rest of the problems you don't really care about. So that's what this system does. It takes inputs. So what are the various features, right? It takes inputs from error stacks, trace data, problem description, and then it basically takes all of these issues and generates something called a bug tree. A bug tree is sort of like a cluster of features. In this case, all the various kinds of defects that have similar attributes, and it tries to contribute all these to the feature set. Then it applies logistical regression to this, and the model basically defines the significance of each of these features. And then once you identify the root of this cluster, which is the bug tree, you use this automatically to mark all of the other issues as, okay, this are all duplicates of the same problem. And then this feedback where a human is basically asked to say, okay, is this good or is this not good? So there is there's some amount of automation that can be applied in this process. And at the same time, there's also a human that actually has to go back and say, hey, this was wrongly marked. So this is also a semi-supervised machine learning model. But the accuracy rates for this model are as high as 85% in terms of what it actually closes. So this is adaptive bug search, which is how we identify duplicate issues across the Oracle Cloud, and we close these issues automatically. And those instances get scheduled for patch application. In the next patch application, it will automatically say, oh, all these instances have to be patched. And then you say, okay, this is on one of the Exadatas, and it seems like 60% of the instances are affected. I might as well patch the entire Exadata. So that's how people get a perspective of what is affected, how many users have actually seen this problem, and stuff like that. So this is the adaptive bug search. Another one that's interesting is signatures. We generate signatures, right? Now this is less of machine learning and more of like a hierarchical temporal management system, where you basically generate a hierarchy and you look at these exceptions, and then you identify these exceptions and generate a chronological event or order within which these exceptions are generated. So this is basically finding what the FSA is for all these various events. And then you generate the LCS, or the longest common subsequence of anomalous entries. A much more log-based view of this is like this. Now, this is a log entry for a clusterware log, right? So the first thing we do is we generate the knowledge ID. Okay, the knowledge ID is basically a unique line for these log files. And then it tries to identify the signature. Signature meaning, so think of it this way, right? So you wake up in the morning and you leave at 9 o'clock. You catch a train and you go to the office. And this is a sequence of events that happen. You wake up in the morning, you have your coffee, you brush your teeth, you catch a train, and then you go to the office and you have a meeting with the customer, okay? The first case is you do everything, you go to the customer, sign the deal, and it's great. So that's a signature for me. So if I wake up at 9, I go ahead and I brush my teeth, I have my coffee, catch a train, go to the conference room, impress the customer, deal is signed. The next day I wake up 15 minutes late. So I decide I'm not gonna have my coffee, but I brush my teeth, catch the train, but I sleep off in the conference room. So the customer is like, this guy's not interested in selling me anything. I'm out of here. So I know that's signature, and that doesn't work. The third day, I again wake up 15 minutes late. This time I say, oh, I'm not going to brush my teeth. I'm just going to have my coffee and head off into the train. And I go to the conference room, and the customer runs out because of bad breath. So that's the third signature. So I know I'm generating these signatures, right? The signatures basically are a sequence of events. And basically, after this sequence of events happen, either something bad happens or nothing happens. And I generate these examples of these events, and then I do a simple probabilistic match across these events. So like, we predict if a database instance is going to crash. We predict if a 4031 is going to happen. A 4031 is basically a shared pool event where I'm running out of memory. So if I'm running out of memory in a database, sometimes the database recovers, sometimes the database doesn't recover. I try to find the odds if a database is going to recover. And remember, this has to be generated for different databases, different Exadatas, the signature is different. So it's not like I generate this model, I train it once, and I push it across all the Exadatas. Different Exadatas, different versions, like if a flash version of an Exadata works differently from a disk-based version of an Exadata, or an X8 works differently from an X6. So these models need to be retrained whenever I'm running this across different Exadatas. So this is signature matching. The next one is,
hey, Sandesh, just a real quick question on that, and also just kind of watching the clock here a little bit. But you're doing great, but so I'm not going to delay you. But okay. Are you doing partition by when you do the different? You said it's on this database. That's do you use the partition by at all to do that?
No. So this is different. So these models, they basically take the input characteristics are depending on what kind of Exadatas I'm running them on, what database versions I'm running them on. Those are the
okay. So that's just an input rather than a separate stream. Got it.
Correct.
All right.
Well, everything at the back end is stored in partitions.
Got it. All right.
The actual data models, all this stuff is stored in partitions at the back. But the inputs are, you're scanning for different Exadatas, you're scanning for disk characteristics, memory, you're looking at number of databases packed in the system, you're looking at number of exceptions per database log. There's so many other, those are all the inputs that we use as attributes.
Got it. All right, thanks.
This example has a lot less machine learning in terms of like probabilistic matching. It's just signatures, right? So there's this thing, it's called HTMs. It's a very popular and an old concept. There used to be this paper on Numenta on how to basically work with HTMs, but it's pretty cool. So I can enter a log line and it's going to tell me what's going to happen in this log line, like 10 plus events from now, based on the training I've done in my system. So if it's a 4031, is the database going to crash? If it's an OR 600, 2060, what is this going to result in a corruption in a database instance or not? So if this is a 4030, is my query going to complete before it runs out of PGA space? These are kind of things it helps me predict. All right. So how do you do performance, and how do you predict a system is basically going to crash way before it actually crashes? This is a very simple, but it's one of the most powerful examples of where something that could take like days to analyze is something we could look at and find in minutes. So it's actually very simple. We take all this input data, we look for faults, we try to identify what's causing the problem, and then we try to generate a prognosis. Here's a simple example of this input where we have a whole bunch of inputs or probes, and then based on each probe, there's a certain normality associated with this. We basically use Bayesian or naive Bayesian methods for this. And as you can see, for different characteristics, we just define the normality. We look at what the values are. We look at what the residual values are, and we predict that for this system, this is what's actually going to cause the problem or not. So this is how we look for performance issues. So whenever there's a performance issue, like in this case, we're having network bandwidth utilization issues, packet issues, we basically conclude based on these 4 important symptoms that this is a network bandwidth utilization issue. So this is purely performance on the database and the Exadata side. And we can predict when something is having a log file sync issue, or when something is having a log file parallel write issue. Is this a disk issue, or is this that you've basically running too much of stuff on that box and the log writers are not getting enough CPU? We use this to predict, and this is called Cluster Health Advisor. This is also available as an on-prem option when you're installing this with the Oracle database. But this allows us to predict health issues with the database. This is an interesting example for workload. This is actually one of my favorites of lately, which we've been playing with. And again, before I had shown you also, there was another workload prediction example, but that was slightly different. That allows me to predict what SQLs are causing problems. What this does is not just what SQLs are causing problems, it also allows me to pull and run analysis via ADAT and some of these other ASH diagnosis tools that are available for us. How does this work? We capture metrics for each of these dimensions in ASH reports, and then we basically run this through SVM, outliers, class 1 SVM, or the standard. We have standard 3 or 4 models that we run this against. You need at least 7 days of data and about 92% of model confidence, and then we flag this for anomaly detection. What is this used for? Say, for example, I'm running a workload, and my workload is a combination of CPU utilization for 90% for say 6 minutes. Is that normal for me or not? This model helps me find that out. Sometimes it's normal for me to run at 100% utilization for 6 minutes. Sometimes it's not normal for me to run that. That's what this model identifies, and whichever anomalies are identified, it automatically generates ASH and AWR reports for people to look at. Now, this is something purely that an ops person can look at or does not want to look at. But today, because there's no way for us to find out, this creates an adaptive baseline. So we can say if it's 2 times the normal behavior of this customer system, that the performance is constantly spiking and the customer doesn't have, say, auto scaling turned on, then we have to go look at it and see if this customer is having a problem, or is the customer just doesn't care and I'm not going to pay any more for these CPUs. I'm going to run at 100%, but I'm going to have severe degradation on my SQLs that I'm running. So that's what this use case is all about. So you take the actual values, you find the anomalous values, you forecast the upper and lower range, and you forecast what the future values are. And you notify the admin that, hey, by the way, most of the stuff you're running, I think you need to buy more CPUs because you're constantly peaked at 90% no matter what you do. And it would be great if you double the number of CPUs because you can get this stuff done a lot more faster. Now the user can say, I don't care, I don't want to pay any more money. I'm happy just running this stuff and let it take how much ever time it wants to take. Or I can say, by the way, these users are using more CPU ever since they initially provisioned their instance. They probably need their own box, or they need to be put in a high CPU utilization category. And we move them to another box where they're not grouped with similar users that are using high CPU. So it's a placement problem, and it's also for us to generate these anomalies. So this is kind of like a dummy user screen, but this is what the actual screen also looks like, where it shows all the tenants and which instances are ASH CPU bound, which ones have more DDRM weight, which ones are CPU capacity related, which ones are which boxes are violating any critical issues or battery rate failures, all rate controller battery failures. All of these things are documented for us. In a couple of clicks, I can find out for which tenants what is going wrong, and if any of these something that I need to do for this. So this is the actual screen. The data is actually faked in this because I can't put the real data. And at the same time, if as an ops person, I can click and find the recommendations on the right-hand side as to what am I supposed to do with this. This has been presented many, many times, and there's this thing where we can automatically identify the best indexes, and we use reinforcement learning in combination with an expert system that tries to figure out what indexes are created. This is not an AI ops case, but this is another case where machine learning is used. I've got all these slides from Charlie, and these are basically all the algorithms that are available as part of Oracle Machine Learning, and that we use Oracle Machine Learning for some of our use cases. So the cool thing that we've always realized, right, is that if you're basically taking data that's sitting inside an Oracle database, and a lot of us actually are in that category, and I've seen a lot of people waste time by just pulling that data out, putting it on a disk, loading it as a CSV, doing a Python, doing a pandas data frame, running a whole bunch of stuff against it, and running it back out to CSV, and then pushing this data back into the Oracle database. I've seen a lot of people waste time on moving data back and forth. So the thing I've realized is if the data is already sitting in the database, it's probably the best thing to do is just run the algorithm right in the database itself. Do not try to move the data out. Do not try to, because you spend a lot of time in terms of space, moving data actually. So because in our case, we're looking at petabytes and petabytes of data. So for us, it's highly inefficient if we actually have to move this data. You know, all these things look great in examples where someone just shows you, oh, here's an example, load in a notebook, some CSV file, a couple of 100,000 rows. All looks great. When you actually move to practical examples, when you're trying to pull a whole amount of data back and forth, it doesn't work very well. So a lot of people just waste time moving stuff and not actually running machine learning stuff. We use a whole amount of stuff internally. So of course, most of us are notebook guys, but I have a guy in my team who loves the data miner UI. I have people who love the Zeppelin notebooks. So there's a couple of Jupyter guys. Some people like RStudio. Most of us are not R guys, but most of us fall into the category of the SQL guys and the Python guys, as well as a couple of guys who like the data miner UI. And obviously, we get data from all sorts of different sources, from object store, from NoSQL data, different kinds of NoSQL data, because a lot of the events that happen on the instances, we basically capture this into a SQLite or a Berkeley DB instance. It depends on which product you're looking at. And then we push all this data out. So we're using some NoSQL on the system so that we have a smaller footprint to store and query against some of this stuff. We're also using Lucene indexes on the server to basically index, so that what we do is if we are looking for a particular event, we can look up the Lucene index. The Lucene index just tells us if this event is there or not. So then if the event is there, I actually have to search through the index to pull it out. But the advantage of having things in these light NoSQL based things on the machine is I have a smaller footprint and I can eliminate use cases where I don't need to push the data out of the system at all. So I'm looking at, say, 50 exceptions. And out of the 50 exceptions, 2 exceptions I really need to analyze. The idea is to filter these exceptions on the system itself and just push out everything else to the object store where it can be analyzed by the machine learning service that's present inside the control plane. So that's
Sandesh.
Uh-huh.
Hey, Sandesh. Hey, Charlie. Hey, I just I wish we had more time.
Okay.
We're running a little bit tight on time. Can you take it in for a landing soon, or?
Yeah. So I had a couple of slides for most of your stuff, Charlie, what we use and what we're looking forward to with some of the AutoML stuff that you were talking about for OML for Pi. And I'll go to the last slides. And also
there's so much good stuff here. It's hard to absorb. Just wish we had more time.
Yeah. So I mean, this is this is a very interesting topic, and I tend to get carried away with this. But
that's why we're here.
So here's a summary, right? So AI/ML for database management is here to stay, and it's all going to be integrated with it. So this is a very interesting space for AI ops. And more stuff that I used to work on for the last 15 years, now it's possible to do more and more with automation using AI/ML. All database diagnostics, that's one thing we've been working on for the last couple of years. All database diagnostics would be in a machine ingestible format. This is already true for most of the stuff that gets generated. Database has alert logs in XML. Most of the components generate some kind of JSON output. So anything that has to be enabled for AI ops should basically be generated in a machine learning format. Modeling and ML infrastructure is becoming standard, which is basically AutoML is the way to go. I know people that have taken up, this whole modeling as a kind of a job category, and they think that running this against different kinds of hyperparameter optimization or running this against algorithms is actually a job. I've actually seen AutoML, and you've seen some of the speakers today use tools where you don't really need to know what algorithms you're running, that automatically performing cross-fold validation across different sets of data, so you see what your test data splits are. All of this stuff is going to basically become automated using AutoML. So if you don't know any of this stuff, that's okay. AutoML is there for the rescue, and you can basically get done with whatever you want to do. Getting the right training data matters. One of the biggest things I've seen when, at least our machine learning projects that fail is basically we're not training with the right data. So obviously it's garbage in, garbage out. And the more you move from machine learning algorithms towards neural nets, it becomes even worse, because neural nets are extremely sensitive to having the wrong data. Lately, I've been seeing this is actually pretty cool, is models are getting better with sparse data. Normally you need a huge amount of data to train. Nowadays, with all sorts of different methods like active learning and transfer learning, models are getting better with sparse data. So in other words, the time to market for a model is getting shorter, significantly shorter as compared to what it was like 3 or 4 years ago. The number of patents that have been filed in the last 4 or 5 years in machine learning space dwarfs the entire duration of when machine learning as a topic has been active since the 1940s. More processing will move closer to data. So this is what I was telling you earlier and even I know Charlie and all these guys talk about this stuff very, very commonly, right? Is people spend too much time moving data, creating data replicas, creating data silos, and then the data kind of goes out of sync. And you spend more time managing the data than actually doing the analysis of the data. So move your processing closer to the data. I cannot emphasize this anymore. This is so many headaches for us have gone just because we moved more processing closer to data. Wherever your data is, whatever platform it's in, run the analysis on that platform right there. If it's in Oracle, if you've already got views, if you've already got materialized views and stuff like that, you can run most of this analysis on top of this. AI ops is a combination of automation and machine learning. And one thing I've seen, and a lot of people love this, they love to apply deep learning to everything. Oh yeah, let's go for LSTMs and all of that stuff. In our case, LSTMs have fallen flat for many, many of the use cases. Simple classification, clustering, and regression tends to work like 90% of the time. And these machine learning algorithms are a lot more resilient to data quality problems as compared to deep learning. So deep learning is great for facial recognition, Facebook kind of stuff, translation, voice processing, and all of those kind of things. But when you're applying this for AI ops data, simple ML tends to work a lot more better. The models converge a lot more faster. With that, thank you so much for your time. Sorry, Charlie, didn't mean to go over that much.
Thanks, Sandesh. It was very informative.
Yeah, thank you. I wish we had more time for this. We're learning. As I said, we're all unprofessionals here, except for Carrie, who knows what she's doing. But we're trying to figure out how to schedule these things better. We probably should have allocated a little bit more time for a few of these things. But we wanted to have it, packed with information. So thank you. That was excellent. I was looking at the questions, Sandesh, and I think you addressed them all the way through there. So I think you've already addressed those. And if you still don't think that he's addressed your questions, please put them in Slack. Sandesh and all of us will be watching this